Good morning. Let's continue. In the yesterday's class, we have talked about min terms and max terms. Now today we will see unit function. What is unit function? A switching function is said to be unit if no variable appears in both complemented and uncomplemented form in the minimized expression for the function. Means, let's say there is a switching function or Boolean function, and after minimizing, if any variable appears only in one form, either in uncomplemented form or complemented form, such function is said to be unit. For example, consider this. This is the final minimized expression, and if we notice, A appears only once and B appears twice. In both the places, B is in uncomplemented form and D appears only once. So what all variables that are appeared in the final expression, all of them should be either in uncomplemented form or complemented form, but they all should be in only one form. I mean any variable, we are talking about the single variables. This expression, minimized expression, is unit function or innate expression, innate function. And second example, this is the minimized function, and how many times A is appearing in the minimized expression? 2 times. In both the places, A is in uncomplemented form, and B is appearing 2 times, 2 places. In both the places, B is in complemented form. Doesn't matter in which form it appears, in all the places the form should not change. And D is appearing twice. In both the places, it is in uncomplemented form. So second example is also innate function. Now look at the third expression. Third expression is containing 2 terms. This is the ABC bar plus ABC, and if you notice, there is nothing wrong with A and B. A is appearing twice. In both the places it is uncomplemented, so is with B. And what about C? Here C is coming in 2 places. Here it is in uncomplemented form, whereas here it is complemented form. This type of expression is not unit function. Maybe there is possibility for further reduction. You can notice, you can take AB common, so C bar plus C becomes 1. So finally it can be reduced further to AB. Now here, if you consider this is unit function. So that is what unit function is. Now let's see that unit function is further classified into positive unit function and also negative unit function. Now what is positive unit function? A switching function is said to be positive unit if all the variables appear in only uncomplemented form. In the minimized expression, if all the variables A, B, C, all the variables should appear in only uncomplemented form, then it is said to be, then such a function is said to be positive unit function. For example, if we consider this is the minimized expression. How many variables are appearing in the final expression? A, B. There are 2 variables. All the variables, A is appearing in uncomplemented form. B is also appearing in uncomplemented form. D is also appearing in uncomplemented form. So it is positive unit function. It is positive unit function. And if you consider this, the last expression, AB, it is also positive unit function. Another one is negative unit function. What is this negative unit function? A switching function is said to be negative unit if all the variables appear in only complemented form in the minimized expression. Let's see. And can we say the second example, an negative unit function, a negative unit function? No. Here A is appearing in uncomplemented form, B is appearing in complemented form. According to the definition of negative unit function, all the variables should appear in complemented form. Here A is uncomplemented, B is complemented. So it is not negative unit function. It is simply unit function. It is not negative unit function. Of course, it is unit function. If a function is not unit, it is said to be non-unit function. If it is not satisfying the definition of unit function, then such function is said to be non-unit function. Next, this is the next topic, canonical form of representing functions. So what are these canonical forms? We can take function and minimize it, or you can modify the function also. If I minimize the function, I get one final result. If you minimize the function, you will get some other final result. These two need not be same. Although they are correct, what I have done is correct, what you have done is also correct, but the final result that I got is not necessarily equal to the result that you got. Logically they are right, but in terms of expressions they may differ. Although logical result is same, means there is a possibility that the same function can appear in different forms. That happens very frequently. But here we are looking for a unique representation of the function. Means if I represent a function, or if you represent a function, or somebody else represent a function, for all of us we get the same answer. It is same both logically and also expression wise. We are looking for such a representation, and that representation is called canonical representation. Now in canonical we have two types of representations, canonical sum of products, that is one way of representing. The another way is canonical product of sums. Canonical product of sums. The first one is also called disjunctive normal form. The second one is also called conjunctive normal form. Now let's see what are these, how to represent a given function in the canonical form. You can represent either in sum of products, canonical sum of products, or canonical product of sums. Now see, a canonical form is a unique representation of a function. We can derive two canonical representations directly from the truth table. If truth table is given, means if there is a problem, if you understand the problem and if you move towards solution, as a first step we have a truth table. We develop a truth table for the given problem. That is what is truth table. Truth table, what details we have? Truth table contains the output for all the possible input combinations. That's what a truth table is. Directly from the truth table we can write down the canonical form, both sum of products and also product of sums. That is one thing. The other thing is, if truth table is not given, directly function is given, then too we can write down the canonical forms. That we will see later. We'll begin with truth table. If truth table is given, how to write the canonical sum of products and also canonical product of sums. Let's see one after the other. We begin with canonical sum of products. Now how to write down the canonical sum of products. Now these are the steps given. From the truth table, identify all the minterms. So we know what a minterm is. A minterm is sum of terms, some terms where the output for which the input combination is produces 1, corresponding to rows for which the output function is 1. Take the sum of all the such minterms. Take sum of all such minterms. We can write down the canonical sum of product expression in a compact way. This we will see little later. Now consider one example. This is the problem. Given problem is find out there is a problem. Means we have to develop or we have to design a circuit which is full adder circuit. Full adder means it takes 3 input bits and produces 2 outputs. One output is sum, the other output is carry. Carry is represented C0 because C is already used for input variable. So we are using C0 to differentiate this with this C. And sum is given label S. And we have done it 2 times before. This is ABC and these are possible input combinations 0, 0, 0, 0, 0, 1 all the way to 1, 1, 1. And for this input combination, sum is 0, carry is 0. Let's say for this input combination 1, 0, 0, sum is 1, carry 0. For this input combination 1, 1, 0, sum is 0, carry 1. And for the last one, sum is 1, carry 1. This is the truth table that follows the problem. This is the first step towards the solution. Means after understanding the problem, if you move towards the solution, this is the first step that we do, which is called truth table. Now we can write down the canonical form. Right now we are looking at canonical sum of products. Canonical sum of products. Right? Now this is sum expression, this is the carry expression. Both are in canonical sum of products. It is sum. This is one term, this is one term, this is one term. All of them are sum of. Each term is a product term here. This is one term, this is one term. Each term here is a product term, which is sum, which is summed up to get some output. Here also, each one of these terms are products, and we are summing them to get the carry. So, and it is a canonical form. It is the canonical form for the sum output. It is the canonical form for canonical sum of product form for the carry output. Now let's see. Now according to the rules just we said, what we have to do is we have to identify, let's say we are writing the canonical sum of products for sum output. Now look at the truth table, the sum column, sum output column. This is the column. And we have to identify the minterms, true minterms. True minterm is a minterm for which the output is 1. False minterm is, it is a minterm for which the output is 0. So this is true minterm, and this one is also, this one as well, and this one as well. So there are 4 true minterms. And we have to write down, we have to add all those minterms to get the canonical sum of product. We have to sum up all the true minterms to get the canonical sum of product. Now what is the minterm for this combination, for this input combination? Minterm means if 0, 0, 1 means A bar, B bar, C. That's what we have written. A bar, B bar, C. We have to sum all the minterms. Plus what is the second minterm? This also produces, this combination also produces sum 1. So what is the minterm associated with this? A bar, B, C bar. That is the second minterm. Plus we have to sum all the minterms. So this combination is over. This is also over. This one. So A, B bar, C bar. So this one is A, B bar, C bar. And the last one, A, B, C. So this is A, B, C. So we have written the sum of all the minterms. So sum of all the minterms is nothing but the canonical sum of product. Okay, this is the canonical sum of product. If we have something like this, it is easier to implement such circuits. Later we will see. Although it is, of course, we can simplify it further if it is possible. Next, let's write down the canonical sum of product for carry. Now this is the carry. Now identify for which input combinations the output is 1. Here output is 1, here, here, and also here. So this forms a true minterm, right? So what is the true minterm? A bar BC, that is this one, A bar BC, A B bar C, A B bar C, and this one also A B C bar, A B C bar, and for this one A B C. So after summing up all the true minterms, what we get is a valid canonical sum of product. That's what we have said here. From the true table, identify all the minterms corresponding to rows for which the output function is 1. Take the sum of all the minterms. Take the sum of all the minterms. So we can write down the canonical sum of expression in a compact way. So instead of writing this whole thing, we can use compact representation, that is this. S equal to, since all the terms are summed up, this is the summation, and which terms are there in the expression. See, A bar B bar C, this is this expression. Now for that, what we are doing is we are giving a decimal representation for all the input combinations. For this input combination, what is the decimal representation? 0. 0, 0, 0 is nothing but 0. 0, 0, 1 is nothing but 1. So for each combination, you write down the decimal representation. So we use decimal representations in the compact form instead of using the literals, instead of using the minterms. So S equal to summation A bar B bar C. This corresponds to this combination 0, 0, 1, whose decimal equivalent is 1. So this represents 1. Next one, this one corresponds to this combination whose decimal equivalent is 2. So this represents 2. And next one is this one, for whom the decimal equivalent is 4. So this one is 4. And in the same way, ABC, this one, which is 1, 1, 1, whose decimal equivalent is 7. So instead of writing the minterms directly, we write down the corresponding minterm decimal equivalent. Minterm decimal equivalent for A bar B bar C is 1. The minterm decimal equivalent of the minterm A bar B C bar is 2. Decimal equivalent of the minterm A B bar C bar is 4. Decimal equivalent of the minterm A B C is 7. Like this, we write down the compact product sum of products. It is sum of products. Each term is a product term here. All those product terms are summed up to get the canonical sum of product. In the same way, we can write down the compact expression for compact form of sum of products for CO. So sum, this term corresponds to decimal equivalent 3. For this one, it is 5. This one 6. This is 7. So you put them in brackets. It is just compact representation of the canonical sum of products. Now let's take another form of canonical, which is product of sums form. Product of sums form. Now in the product of sums, what we do? From the true table, identify all the false maxterms. So here, instead of identifying the true minterms, here we have to identify all the false maxterms. False maxterms means, maxterm means a sum term. We all know, according to the definition given to maxterm, a maxterm is a sum term and it has to be sum term which contains all the literals. That's what maxterm definition. That's what a maxterm is by its definition. Now false maxterm means the sum term which produces a 0 in the result. That is the false maxterm. Now we have to identify all the false maxterms corresponding to rows for which the output function is 0. That's what the false maxterm is. For each false maxterm, for each false term, form a sum term where all the variables will appear in uncomplemented, in brackets complemented form if it has a value 0. If it has a value 0, we take its uncomplemented form. If its value is 1, we take its complemented form. We will see what it is just now. In the row, we can write down the canonical sum of product in compact way. This is the compact representation. Now let's see, take the same example of a 3-bit adder, and this is the truth table of the 3-bit adder. Now instead of writing canonical sum of products, we are writing canonical product of sums here. Product of sums. Each term is a sum term here, or max term. We are taking the product to get the final answer. This is the sum representation, this is the carry. Now what we have to do in order to get canonical product of sums is, we have to identify the false maxterms. Means false maxterms means the input combination for which the output becomes 0, not 1, becomes 0. Here we have a 0, here we have a 0, here also, and here also. For 4 combinations, the output is getting 0. So now what we have to do is, for which combination the output is 0 for this combination, A0, B0, C0. Now if A is 0, we have to write its uncomplemented form. A is 0, for B is 0, C is 0, we are getting output sum S0. So for A0, we have to write, if A is 0, we have to write its uncomplemented form. That's what we have written here. Uncomplemented A plus, we are writing the max terms, plus max terms means sum terms. B also 0, so write uncomplemented form. C also 0, we write the uncomplemented form. Since it is the sum of products, sum of products means this is one sum term, this is another sum term, product operation comes in between, and operation comes in between. So now identify another input combination which produces output 0. So there is another combination here. See, this A term is appearing. For A is taking 0 here. If A is taking 0, what A becomes? A itself. If A is 0, A comes out as A in forming the sum terms. Next, B is taking 1, so we get B bar. C is 1, so we write C bar. Dot, another combination here, what we write, 1 means A bar, so A bar plus B plus C bar for this combination. Similarly, for this combination, A bar plus B bar plus C, because C is taking 0, so we write C, just C, not C bar. So A bar plus B bar plus C. So when you multiply all the max terms, all the possible max terms, 0 false max terms, that forms canonical product of sums. This is the expression for sum. This is the canonical product of sum expression for CO, which is carry. Now let's see how do we get. There is one combination here which produces 0. There is another here. There is another here, and this is the last one. So we are getting, A is taking 0, B is also taking 0, C is also taking 0, and producing C 0. So A plus B plus C, A plus B plus C into, what is the next one? A plus B plus C bar, A plus B plus C bar into, this is also the output term, false max term. False max term, A plus B bar plus C bar. Sorry, A plus B bar plus C, A plus B bar plus C into, this is the last one, A bar plus B plus C, A bar plus B plus C. This is the canonical product of sum for output carry. These two can be represented in compact way like this. S equal to, since these are some terms which are multiplied, this term is multiplied with this one and this is also multiplied. So product operation is happening taking in between all these terms. So this is product symbol, and write down decimal equivalent. What is the decimal equivalent for this A, B, C, A plus B plus C? This corresponds to 0. So we write down 0. In the same way, A plus B bar plus C bar. So A plus B bar plus C bar. So this is decimal equivalent 3. So write down 3. And for this we have 5. For this we have 6. In the same way, we write down the compact representation for canonical product of sums. That is shown here. Pi 0, 1, 2, 4. 0, 1, 2, 4. So this is our compact representation, and this is our canonical product of sum representation. Now see, let's read this again. Form the truth table. Identify all the false max terms corresponding to rows for which the output function is 0. For each false term, form a some term where a variable will appear in uncomplemented form if it has a value 0. If it has a value 0, we write its uncomplemented form. If it has a value 1, we write its complemented form. This is the key thing. Otherwise, you will write down completely opposite canonical form. Next we will see algebraic procedure to obtain canonical sum of product. Now algebraic procedure means if truth table is not given, if a function is given, how to obtain canonical sum of product, that we will see now. These are the steps. The first step says examine each term of given sum of products expression. If it is not a min term, go to the next step. If it is not a min term, go to the next step. For all missing variables xi, multiply the term by xi bar plus xi. We all know xi bar plus xi always equal to 1. Multiply out all product and eliminate redundant product terms. These are the steps. Let's understand with some examples, and we will come back to these steps again. This is the example. There is a function, a Boolean function or switching function having 3 variables a, b, c, and this is that function. This is that function a b bar plus b plus a b c, and we have to represent this function in the canonical form, canonical sum of products. That is sum of products, right? Canonical sum of products. This is the shorthand of sum of products. So sum of products means all the sum term contains all the min terms. Sum of products means sum of all the min terms. Min terms means sum of all the product terms, right? So of course it is sum, but is it a min term? Canonical representation means, canonical sum of products means each and every term should be a min term. Is it a min term? Is it a min term? Is it a min term? This is a min term because it is a product term and it is having all the literals. So it is a min term. Is it a min term? No, because the function is having 3 variables. This term is having only 1 variable. 2 terms are missing. So it is not a min term. Is it a min term? In this term, of course, this is a product term, but A is there, B is also there in complemented form, C is missing. This is also not a min term. In that case, if you want to convert this into a canonical sum of product, we have to do the following. We have to identify the terms which are not min terms and identify which literal is missing. So in the first term, C is missing. So A, B bar. For C, what we do is A, B bar. We multiply this term A, B bar with 1. Multiplying a term with 1, does it alter the result? No. So we can do it. So A, B bar. Instead of 1, write the missing literal like this, C plus C bar. The missing literal is C. So we write C plus C bar. What is C plus C bar? Always equal to 1. So AB bar into 1, where 1 is C plus C bar, the missing literal. So this doesn't alter the result. In the same way, write down for B. This is the only literal that we have. To make it a min term, we multiply it with the missing literal is A. So for A plus A bar, which is 1. B, multiplying B with 1 doesn't change the result. In the same way, C is also missing. Multiply that with C. B into 1 into 1. This one is 1. This one is 1. That doesn't change the result. So another missing variable is literal is C plus C bar. We write like this. Plus there is it is a literal by definition. We write it as it is. Now we use distributive law to expand this. A B bar C, A B bar C bar, and here we get 4 terms. BAC, BAC means ABC, and BAC bar, BAC bar, BAC bar means ABC bar, BA bar C, A bar BC, BA bar C bar, A bar B C bar, and this last one comes out as it is. And if there are any redundancy terms, ABC is happening twice here. So ABC plus ABC results only one ABC. Doesn't matter how many times a term is, the same term is added, that can be reduced to only one term. So ABC plus ABC can be written only once. So finally, this is the expression. You may notice here all the terms are min terms. This is a min term which is a product term. This is a min term which is a product term. It is sum of all the min terms. So it is a canonical representation. Now let's continue. Next, what we do is, in the same way, we look at algebraic procedure to obtain canonical product of sums. You got the previous one, which is canonical sum of products. In the sum of products, what we have to do is, first of all, look at the function and identify the terms in which any literals are missing. And if you find, let's say C literal is missing, multiply the term with C plus C bar. Because C plus C bar is 1, that is nothing but multiplying the term with 1, which doesn't alter the result. Finally, what we get is something like this. The same thing is said in the steps also. You read those steps again and understand it. Last step says multiply out all the product terms. That's what we have done here. Multiply out all the product terms and eliminate the redundant product terms. In this example, we got one term which is twice. ABC is the term which happened twice in this expression. So you consider only one term here and ignore the repeated one. Next one is algebraic procedure to obtain the canonical product of sum, the other form of the canonical. These are the rules, the same rules. Identify the examine each term of a given product of sums expression. If it is not a max term, if it is, then go to the next step. For all missing variables xi, add the term xi into xi bar. Xi into xi bar is 0. If xi is 1, 1 bar is 0. 1 into 0 is 0. So means we are adding 0 to the term in which any literal is missing. Adding 0 doesn't alter the result, so we can do it, and in that place we can substitute the missing literal like this. So this is the function given. This is the Boolean function which is having 3 variables, and this is sum of, this is product of sums. This is one term, this is another term, this is some term, and let's say this is one term whose we are considering its product, right? We are having the product of those 2 terms. Now, if you see here, the function is a 3-variable function, but in this term, we have 2 sum terms only. For this to be a max term, we need one more literal. What is the missing literal? A is the missing literal. So for this, what we do is we write b bar plus c as it is, b bar plus c as it is. Now the missing literal is a. In the place of that missing literal, what we do is we write 0 plus. We add 0 to this existing b bar plus c. Say 0 plus b bar plus c. For 0, we write the missing literal. What is the missing literal here? A. So 0 is equal to a bar. We can write like this. A bar is always 0. So 0 is added with b bar plus c, which doesn't alter the result. So there is nothing wrong in writing like this, because it is this. So we convert a function which is not in canonical product of sum into product of sum form, canonical product of sum form, right? So for this, the missing literal is a. We write like this. For this, what are the missing literals? Only a is present, b is missing, and also c. In that case, what we do is a bar is written like this. To this, we add 1 0 and one more 0. This 0 is for b, this 0 is for c. So 0 can be written like this, b bar, and another missing literal in the first term is c bar. So we write like this. A bar is a bar, this is 0, this is also 0. Adding these two terms doesn't alter a bar functionality. So we write like this. Now after expanding, what we get is, since there are 2 missing literals, we get 4 terms, 4 max terms. This is 1, this is 2nd, this is 3rd, this is 4th. And if we expand this by using distributive law, since there is only one missing term in the second, missing literal in the second term, so we get 2 terms. Now let's see what are they. A bar plus b plus c, considering this, that is one max term. A bar plus b plus c bar, that is another. A bar plus b plus c bar. Next, b is used. Let's use b bar this time. A bar plus b bar plus c. A bar plus b bar plus c. This is this one. A bar plus b bar plus c bar. A bar plus b bar plus c bar. So first time we use a bar plus b plus c. Next time a bar plus b c bar. This combination. Next time, since b is used, a bar plus b bar. Let's use b bar. One time for c, another time for c bar. Like this. So after expanding this term in which 2 missing literals are there, we get 4 max terms like this. 1 term, 2nd, 3rd, 4th, and use this one and expand this one by using distributive law. There is only 1 missing literal, so you'll get 2 product terms, 2 max terms here. 1 term, consider a plus b bar plus c, that is this one, a plus b bar plus c. Next one is, we have used a, let's use a bar plus b bar plus c, a bar plus b bar plus c. See, if we are multiplying a plus b bar plus c, a bar plus b bar plus c, if you multiply these two, we get back this one. There is if you want, you can prove it. It is very simple to prove, right? So now we got each term is a max term here. There is a max term because all the literals are involved here. Each and every term that we see in this line are max terms, and their product of max term is canonical product of sum. Sorry, sum product of sums. This is sum, and so on. And if there are any redundant terms, for all those redundant terms, use only 1. Now, what is the redundant term here? A bar plus b bar plus c. If you notice, a bar plus b bar plus c is occurring here and also here. So write only 1 time for that. So this one, only 1 time. This one. We don't write this because it has already come here. So no, don't write again at the end. This is the final canonical product of sum. So this is the canonical product of sum. Next, a small topic. I will take 5 minutes. I will complete this. Transforming one form to another. If one form of expression is given, how to transform that into another? Let's say sum of product is given. How to convert that into product of sums? Now double complement the given function and apply the De Morgan's law. If you double complement any function, the function doesn't change. And then you apply the De Morgan's theorems. This is the rule to be followed. Complement of sum of true minterms is the same as the sum of false terms. This is not actually rule. This is a shortcut that can be used in reducing the complexity. Let's use some example. There is an example. Now, in this example, what this form is it a canonical sum of product form? Yes or no? Yes, because each term is a min term. This is a min term, 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 and we have sums. So it is a canonical sum of products, and we want to convert that into canonical product of sums. Canonical product of sums. Now let's see. First, this is the function given. This is the function given, which is f. If you complement that function and complement again, will the function changes? No. This expression is identically equal to this result. So these are identically same. Nothing wrong in complementing twice a function if it is useful in doing something. So write down f. This is the entire thing f given. We are writing complement one time and taking complement second time. That doesn't change the result. So what we are doing is, for the expression, get the not of it. Not of it means complement means not function. Now since it is a three variable function, how many combinations are there? For a three variable functions, there are 8 combinations. 0 0 1 1 0 0 0, like that, 8 combinations. Out of 8 combinations, how many are there here? 1 2 3 4 5 combinations. And each one of them is a min term. So each one of these terms represent one input combination, right? And we want the not of these 5 min terms. Now what we get is the remaining 3 missing terms. If you not it, what we get is the remaining missing terms. Otherwise, you can simplify it and you can do normally by using all the rules. It takes a lot of time. Instead, what we can do is, not means these are the min terms, and for the input function, 8 input variables are there. For 8 input variables, 3 input variables are there. For the 3 input variables, 8 combinations exist. Out of 8 combinations, 5 are here, and we have to take the complement of these 5. Means how many remains in the result? 3 remains, only 3. What are those 3? These are the rest. Out of 8, these are the 5. Remaining 3 are written here. This is nothing but complement of this entire thing, which is in bracket. So this entire thing complement becomes this. If you have any doubt, you can do normally by using rules. You will still arrive at the same thing. This entire thing is this. We are not doing it normally according to the rules, but we are using some shortcut here. This is described as a rule. Complement of sum of true min terms is the same as the sum of false min terms. So this is the min terms, sum of min terms. What are the false min terms? These are the false min terms. Take the complement here. Now what is the complement? Use De Morgan's law. What is the De Morgan's law? This sum becomes multiplication. This sum becomes multiplication here. This sum became multiplication here. And when you apply complement to the first term, what you get is this dot, a bar, b bar, c, a bar, b, c. In between these letters, we have a dot. The dot becomes plus. A and the variables themselves becomes complemented. When you complement a bar, what we get is a. Instead of dot, we get plus. B becomes b bar. Instead of plus, instead of dot, we get plus. C becomes c bar. Since we have plus, that becomes a dot operation. A bar plus b bar plus c. A bar plus b bar plus c. this plus becomes dot. A bar plus B, because B bar is there. When you complement it, what we get is B plus C bar. This is completely this step results after using De Morgan's law to this step, which we already discussed. This is how we transform canonical product of sums into sum of products, and canonical sum of products into product of sums.